All right, section 1.3 is evaluating limits analytically. So there's two ways we've evaluated limits so far. Do you remember what they are? Numerically and graphically. Fantastic. So numerically means with tables. Graphically means with graphs. Okay, good. Analytically is going to mean that we're going to do some algebra. So sometimes you'll see this say evaluated limits algebraically. Okay? So some basic limits that you need to know. If you have b and c in their real numbers and n is a positive integer, then the limit as x approaches c of b is b. So this is like saying the limit of 5 is 5. Okay? The second one says that the limit as x approaches c of x is c. Okay, so you're just plugging in the number of the x value you're approaching. I think that somebody asked me in the last section if we could just do that, right? Yeah.
Would the B and C be switched to number 1?
No. I'm going to show you a picture of why each of these works. So give me just a second on this. Just write them down for now, okay? And then the last one says that the limit as x approaches c of x to the n is c to the n. I'm going to show you a picture first, but yeah. Okay, the first one's the easiest picture to draw. On the first one, I'm going to sort of verify this graphically for the most part for you guys. What does it look like if this said, let me write it this way, equation y equals 5. What does the equation of y equals 5 look like? Horizontal line, okay? Horizontal line at a height of, in this case, b, because my number that I'm using is b, okay? What's the y value every point along that line? 5, or b, right? It's the number I've already got. So does it matter what x value that I'm approaching? Not in the slightest, because it's a horizontal line. Okay? That's why the limit of a constant is the constant itself. That's all that says. The limit of a constant is a constant. All right, this one says right here that my equation is y equal x. So again, if I were doing this graph, and the limit is y equal x is the line that looks like this. At every x value along the line, what's the y value? The same thing, because y is equal to x, right? So no matter what x value I'm approaching, that's the same y value that I'm getting close to as well. Okay? 3 is the same kind of thing, right? If I have x to the n, then I'm going to have, so this is y equals x to the n. So if x is approaching 3, then y is approaching 3 to the n. Okay, because that's my equation. And n has to be a positive number for this to work. Or does it say positive integer? Yeah, positive integer for that to work. Okay, there's a few others that are just so wonderfully nice that you'll use them and won't even realize you've used them as you're using them. All right, so the first one is called a scalar multiple. On this one, what you e-value right here, which is sort of inside with the f of x, right, sort of inside the limit itself, comes out in front because it tells us right here that the limit of f of x is L, and then here's your L. Okay, so in a very real sense, what they're saying is you can pull out the b over here. Okay, like scalar multiple. Yeah, basically, because it's a number. Yeah. So if it's a constant, it can just be factored out in front. It can be ignored. You deal with what you've got, and then you multiply by it when you're done.
The L just stands for the limit?
L just stands for the limit, exactly. It's the number that they're using. They're letting L and K up here be the limit values that we're talking about. Number 2 is fantastic. It's saying that if you add f of x and g of x together, and then you take the limit, it's the same thing as taking their individual limits and adding them together. So you add the L and the K, or subtract them. These are both things that you would want to be true. You would want those features to be, easy to work with, and this is basically telling you that they are. It is exactly what you would expect to have happen. The third one is as well, product. If you take two functions, you multiply them, and you take their limit, it's the same thing as taking their limits and multiplying them afterwards. So take the limit after they're multiplied, take the limit before they're multiplied, you get the same answer. Okay? So you get L times K.
So are these things that, like, if we were to write a proof,
They are. We're not going to do what you suggested, as in write a proof, not for these. Mm-mm. But we are going to use these facts in our work.
Okay.
And as you use them the first couple of times, I'm going to show you, hey, look, you're using them. You're using them. You're not even going to feel like you're doing anything because you're going to be like, it's so natural that this is exactly what you would expect and have to have happen. And it is going to happen. You're not even going to notice it happening. Okay? Two more. Quotient. Looks a lot like product. If you divide the two values and then you take their limit, it's the same thing as dividing their limits. As long as one of the limit, whatever's on bottom, is not 0. Okay, no limits of 0 on bottom. That's not going to hold true. So there is an exception. And the last one, the power one, looks a lot like the basic rule number 3 above. It's saying if you have the limit of a function raised to the power n, then it's the same thing as having the limit of the function, which is L, raised to the power n. Okay. So those are all of the properties that we need to find some limits. Okay, so here is the point where Chad, was it you? Are you Chad? You're Chad. Chad, you were the one who in the last section said, why can't we just plug the number in, right? Well, we can now, okay? Okay, and the reason we can is because we have all these properties of limits at our disposal. In particular, the one that's of most value to us was the second basic property. So back on your first page, property number 2 that said the limit as x approaches c of x is equal to c says you can plug c in for x, okay? So let's do that on here, and then I'm going to show you which properties you've actually used that you didn't even realize you were using as you were using them. So what I'm supposedly telling you is that you can now do this. And you get 0 and you're done with no tables and no graphs. Okay, but here's why, okay? The plugging the number 1 in used basic property number 2, right? That's what basic property 2 is. It says I can put this value in. But I kind of almost really used basic property number 3 because there was an exponent there, right? I had to the power, okay? And I used basic property number 1 because I had that plus 1 at the end that I also just carried along because the limit of 1 is 1. So I almost used all 3 of those first basic properties. Or you could say that I used some of the other properties as well. You could say that I used the power property because it was a function raised to the power n. Well, x is in itself a function raised to the power, in this case, 2. Okay? Now, this one down here, number 2, looks an awful lot like it's going to be that quotient one, right? And the quotient one says, I can actually separate this out. So I'll write this out so that you can see it actually happening this time and how it's happening without you doing it. So let me actually show you, written out, what you're using, and then I'll show you what it'll look like when you're actually doing the problems. The property number 4 underneath quotient there said that I can separate this like so. Right? I can separate out for the individual limits. Well, there was also a property that said that I have addition and subtraction. So, I mean, I could actually separate this out with the addition and subtraction like this. And I am being terribly sloppy because I need to go back and put all my limit x approaches, and I'll do that in a second here. Was x and 5. All right, so these were x approaches negative 3.
Sometimes you just get tired writing.
I know. Okay. So then the next piece right here is a product. But it's not really a product, it's a constant multiplier. There's a number that's a number times x, right? Not two functions like that are two variables multiplied. So on this one, I can actually pull the 2 out in front. Okay? And then we can actually use the basic properties, numbers 1 and 2. Number 1 for the constants, that's the 3 and the 5 at the end. So this one becomes a 3 and this one becomes a 5. And we can use basic property number 2 that says I can plug in the number for x. So this 2 at the beginning stays. I have a negative 3 here. And then at the bottom, I have just the negative 3. So I end up with negative 6 minus 3 is negative 9 over negative 3 plus 5, 2. Negative 9 halves.
So when it's adjusted number, it'll always be a number.
Yes.
It doesn't make X to show C.
Exactly. Yeah. So this shows all the steps with all those properties in place.
Okay.
Do you see that?
Yeah, you're just proving.
I'm just showing you that that's how that's coming about. The net result of what we actually are able to do says, because all of those properties are now in place, what I really can do is I can simply jump to the end of the argument. I can go like this. So this is all I'm expecting you to do. I'm not expecting you to go through all those steps, but those properties are what allow you to jump to the end like that. Do you see that?
And when can we not use the properties?
There's going to be one example later on, and I'll show it to you, and you'll see why when we get there. So, yes, ma'am.
Would you prefer us keep it in fraction instead of decimal?
Usually, yes, because not often, but sometimes fractions are cleaner to work with. Often fractions are cleaner to work with because sometimes they end up being like repeating decimals and things like that. And really, in real mathematics, you never see people write repeating decimal notation, like ever. We keep things in fractions. So yeah, for the most part, fractions. If you wrote this as negative 4.5, am I going to get all up and upset about it? No, I'm not. But if you wrote things as negative 4.3 repeating, we might have to have a discussion because that's really just, it's just not what we do in mathematics. So yeah. So, okay. A couple more properties that are some fun, easy ones that make your life nice. If you have a polynomial, okay, so polynomials are the functions that have the powers like 1, 2, 3, 4, 5, and so forth. So you have x to the 5th plus 3x squared minus 2x plus 7. It's a polynomial, okay? So no fractional exponents, no decimals, no radicals, no division of functions. Polynomials. Well, if you want the limit of the polynomial p of x as x approaches c, then that's just p of c. And that's actually what we did on our first example. We just plugged the number in, okay? So it works for polynomials. The second one talks about rational functions, which is what we did for example number 2. It says that when you have a rational number and you take its limit, as long as the denominator's limit's not 0, okay, then you can just plug the number in as well. If the limit of the denominator is 0, we're going to have to talk about what happens later. Okay. So polynomials, rational functions, which was examples 1 and 2, we can just plug the number in. Because all polynomials and rational functions really are is a combination of all those limits we already did. That's all they are.
Okay.
Okay. The next one is composition function. Oh, I'm sorry, I missed one. Radicals first. So if you have a radical, that is, you have like the nth root of something, square roots, cube roots, something like that, then the nth root of x and the limit of that will be the limit itself of the value. In other words, again, you can just plug the value c in. Okay. Now, there's a catch. The catch is that when n is odd, it's only valid. I'm sorry, I get that wrong. It's valid for all c. And then when n is even, it's only valid when c is greater than 0. And you actually know this to be true. All this is saying is if you have something like a square root, which is an even root, you can't have a negative underneath it. Right? No negatives underneath even powered roots. So square roots, 4th root, 6th root, you can't take a negative radical. Okay, negative square root, a negative of a, I'm sorry, you can't take a square root of a negative. Set it backwards. If it's an odd, right, if it's cube root, 5th root, then it doesn't matter if it's positive or negative. So c could be anything. So in other words, if you had the limit as x approaches c of negative 2 square root n, or square root x, that's not going to work. Because you can't put a negative 2 underneath the square root.
So does that
Okay.
do not exist? Or
Yeah, you would have something that does not exist in that case, exactly. And it's kind of like the restriction over here about the denominator not being 0. Now, I'm not telling you what happens when the denominator is not equal to 0. That one does actually sometimes exist, but we'll talk more about that situation later. It could be a whole. It could be an asymptote. There's some other things that could happen when your denominator is 0. So you have to do it differently. Okay, now I think this is our last one of the definition, or theorems, excuse me. The limit of a composite function. If f and g are functions such that the limit as x approaches c of g of x is L, and the limit as x approaches L of f of x is f of L, then the limit of f of g of x is equal to f of the limit of g of x is equal to f of L. This is one of those, the most general way to write down the rule. But when I give you an example, you're going to be like, well, yeah, that makes sense, totally fine. It's just that an example is a very specific case, and I want you to know it works for all cases. Okay? So what is this saying? Well, this is saying that if you had a function inside of another function, in other words, let's say you had a square root, and inside of the square root you had another function x squared minus 7. Okay? So you have a function x squared minus 7 inside of another function square root of x. All this is saying is that as long as these limits actually exist, then we can plug the numbers in exactly like we were expecting to do. Okay, so it doesn't matter if it's a function embedded inside of another function, it still works.
So if it ended up being like negative, then it would...
Right. If you ended up giving, like if you said x approaches 1 on this one, the x squared minus 7 is totally fine, right? I can approach x equal 1 for x squared minus 7. It's a polynomial, no problems. But the answer would end up giving me a number that would be negative underneath the radical, and that wouldn't be fine.
Okay.
Right? Because I would get a negative 6 if I used that. Yes?
Oh, no, you can use f by circle g.
Yes, that's the notation. This one right here is the same notation as f, and there's a little circle that doesn't look much like a circle, but it almost looks like fog, but the O in the middle, if you will, is sort of in the middle of the line, and it's small. So that's another notation for composition of functions, yes. Okay, so let's take a look at an example. The first thing you should try to do, if you're working analytically, truly, is simply plug the number in.
Yes.
Does it work? On this one, no, it doesn't. So if that doesn't work, then what do? You factor. Okay, now this one factors not quite as directly as you might prefer, which is exactly why I picked it. How does the denominator factor?
X plus 3x minus.
Now, the numerator does not match exactly with anything on the denominator. But which one is it actually very closely related to?
X minus 3.
It's the minus one.
Because you
It's actually the
factor-
minus one.
Yeah, negative 1.
Okay, so these two are not exactly the same, but they are the two that are the most closely related. And the reason why is, if I multiplied one of them, not both, but one of them by negative 1, I would get the other one. Right? I can't do that with the x plus 3. If I were to multiply x plus 3 by negative, it still wouldn't be the same as the other one.
Yes.
Okay? So the two that are highlighted in red are the same, except one of them is multiplied by a negative 1. So I am able to factor these out and reduce them as long as what remains is a negative 1. Right? It's like when you factor and you had something like 16 over 22 and you divide them both by 2 and you write down what's left over. Well, I'm dividing both of these by x minus 3 or x plus 3, and a negative 1 is left over. Okay? So what do I have left over? Well, I have the limit as x approaches 3 of negative 1 over x plus 3. Can I plug in 3 now? Yes. Negative 1 over 6. Now, a word to the wise, and this will be our last word to the wise because we're running out of time. This notation, actually I should even highlight all of it. All of this notation will not disappear from your work until you physically put the number in for x. Every step will have that notation on it. Okay?
You can't just write like equals.
No, because if you write equals and you leave the limit off, it's not actually equal. Okay? Every step has limit on it until you actually plug in the number for x. Okay? So we're not going to do the next problem, but you just tell me, what do you think we're going to end up probably having to do on the next problem?
Factor.
Probably going to end up having to factor it, right? So this will be some of the practice on factoring that we kind of alluded to at the beginning too.